Right. So are there any questions about this? This is something I skipped some steps, so there could be some parts that are unclear for this derivation. Getting this equation, but you can do it at home. It's very, very straightforward. One thing to keep in mind is that the time derivative of u is the derivative of u with respect to theta and theta dot. Right? And you get these results. These are just classical results. I'm not going to prove them. And there are some other properties of the conic sections, namely of ellipse, that we are going to use. So let me just draw an ellipse and denote a couple of things here. I will refer to them. So let's say that I have an ellipse. So as you probably know, an ellipse has two foci in the center. So let's call this F prime and F. So our planet is going to go around the sun, where the sun is going to be at one of the foci. The other five focus is called the pulse focus. So this one is called the major axis of ellipse. And A is semi-major axis, so half of this. That will be this one. And likewise, half of the height is going to be B. This is the semi-minor axis. Minor axis. This distance here, if I take the focus and take a perpendicular line segment and hit the orbit, that P is called the semi-lattice rapid. Something I refer to from time to time. For an ellipse, that is equal to A times 1 minus E square, I believe. Maybe square root of the C square. No, it's A times 1 minus E square. So distance of this from the center is A times E. And no, sorry. Which one is it? So this one is A 1 minus E. This one, so this distance is A1 minus E. This distance is A1 plus E. This distance is typically called for an orbit the periapsis distance or pericenter distance, and this one is the upper axis or upper center distance. So this point of closed approach is the periapsis, and this one is called the upper axis. These are just names. As I said, they have been studied very deeply for many, many years. Now, sometimes the object at the center, the attractive mass has a name, like sun. Then this is called perihelion and apohelion. If it's Earth, it's perigee and apogee, and so on and so forth. Okay, I think for Jupiter it's perijovian, perihelion, something like that. Right. Okay. Anyway, so the equation we get is this, and we take this and turn it into, again, the expression for R. And just write this down and take a look at number of properties. So R is going to be L squared by MK, notation, plus 1 plus E, cosine theta minus omega. Now, we can immediately tell that this is going to have a minimum and a maximum, and because you know how the cosine function behaves, right? So when denominator is maximum, this is going to be a minimum, and denominator is minimum, it's going to be a maximum. This is some number between 0 and 1, so you can't overgo. It's always going to be positive, and the denominator is going to be a maximum, and this cosine is 1, right? And this is 0. and that corresponds to R min. So R min is going to be L squared by mk divided by 1 plus E, and R max is going to be L squared by mk over 1 minus E. Okay, so this is what I refer to as the periapsis and apsis order as distances. So A times 1 minus E, A times 1 plus E. Right. Now there's another way to get these, and it provides some nice properties. Oh yeah. So let's say that this is R min, and this is R max. First of all, A, the same major axis, is going to be R min plus R max over 2. It's a non-property of ellipse, and it just immediately follows. You just add these up. Something not so well known is that this is the arithmetic mean. The semi-minor axis is the geometric mean. Then the property of ellipse. It can be shown, but I'm not going to bother proving any of these results. Now I can start with my energy equation. Let's get these in another form so we can identify these numbers. So this is one of the integrals of motion plus R, and this one R dot is you remember the radial component of the velocity, and this one is the tangential transverse component of the velocity. So I can rewrite this. Again, I'm going to need to erase this. Hopefully, you can look this up. So this just becomes a half and PR squared plus a half. So VT squared is we're going to write this as MR VT squared over MR squared plus V of R, and we recognize this as the magnitude of angular momentum. Half PR squared plus a half L squared by R squared, our centrifugal barrier, minus the Kepler potential is equal to E. Okay. Now we are going around in an ellipse. Okay, let's say focus. Now what happens at this minimum distance and maximum distance? What happens to these quantities? Now what happens to radial component of velocity in particular? When you're at minimum R, what happens to R dot? It's 0. Right? Temporarily, just go over some minimum. And same thing for R max. The radial component of the velocity vanishes. So let's write it this way. And so I'm going to say at apsides, I think that's the plural for this, E is equal to a half L squared by R squared minus K over R. So I can find, so I can take this, multiply this by R squared and turn this into a quadratic for R, and I can find the roots. But I don't have to find roots. There are some relations regarding roots, in particular, the sum of the roots, we can write directly in terms of the coefficients of this quadratic equation. By looking at the roots are, okay, so let's say that roots are R min and R max. And A is R min plus R max over 2. And by checking out the sum of the roots from your knowledge of quadratic equations, this turns out to be minus K over 2E. This is a very important result. The energy only depends on the same major axis of the orbit. It doesn't depend on eccentricity. same major axis determines the energy of the orbit. Eccentricity has nothing to do with. What does eccentricity do? Well, it has something to do with the angular momentum. Those are the two integrals of our motion. They determine the shape of the orbit. But only same major axis is associated with energy. Eccentricity does not enter. So, and this is important, but I'm not going to write this down because I don't have that much space. Now, using this, we can also rewrite our energy equation. This form that this is going to become useful. K over 2a is a half mv squared minus k over r. Okay. This is a very commonly used equation that you use to take and manipulate this and find v as a function of r, r as a function of b. Given the same major axis, you can carry this out. Okay. Now we have, let's raise this. The area of the ellipse. Do you know the formula for the area of the ellipse? You can almost guess.
Pi AB?
Yeah, it's pi A. Because an ellipse is nothing but a compressed circle. Right. So you move one axis from A to B, and you get this one. Okay, now let's recall, excuse me, dA by dt. We already calculated this. Is a half L over m, where L is the magnitude of angular momentum. So this means over one period, we are just going to sweep the total area. So I multiply this by the period. Okay. So this is my rate. This will give the total area by AB, but this one is going to be pi a squared 1 minus b squared by a half. Again, by a property of ellipse, that this is equal to a 1 minus e squared to a half. The same major axis, this same major axis times 1 minus e squared to a half. Okay, but then I can pull my period out and do some manipulation. So t is going to be 2m by L pi a squared, sorry, L over mka to a half, and this gives 2 pi a to 3 halves square root of m by k. Okay, so this is perhaps not the best way. I just did this at home. That would be more straightforward ways to do this, but it's just algebraic manipulation. So the expression for t is proportional to some constant times same major axis times 3 halves. This is Kepler's third law. We usually write this as a cubed by t squared is constant or something like that. At least that's the way I always think about this. A corresponds to some kind of average distance multiplied from the sun. Is that the average distance? Is that the time average? So if you do this over one period, is this equal to A? So it's not an unfair question because you have seen this before. Where did you see this before? The average of R. What if I put a 0 here? What's a
Expectation
0?
value?
The expectation of R, is it equal to the bore radius? it's not. There is like 1.5 or something in front, but this is correct. Yeah. So if you take the expectation of 1 over r, it is equal to 1 over. So it is an average in some strange sense. But when written this way, when you refer to the same major axis as an average distance of the planet, this is absolutely correct. Okay. Now these are just properties of the ellipse. If you don't know them, then you get stuck, but these are written in all geometry books. Now, one quantity that we can define, so we can write our r as a times 1 minus e squared, 1 plus e cosine theta minus omega. And I'm going to write this as a 1 minus e squared over 1 plus e cosine f. This f is going to be first of a number of anomalies that we are going to define. This is the true anomaly. And it's just your angle that your position vector makes makes with some major axis. Major axis terms. And so we can get rid of one of the integration constants by choosing your coordinate system appropriately. I can take the expression and it's not very helpful. I'm not going to introduce this, but another anomaly that I want to introduce that is very commonly used is the eccentric anomaly. It is defined in the book in a funny way, but completely algebraically. It is a very nice geometric interpretation. So I'm going to show you that one. Let's say that you're on an elliptical orbit, okay? And this is the center. This is my focus. What I'm going to do is let's draw some coordinate system like this. I'm going to draw the so-called circumscribing circle. Right, so this is a circle that is tangent to the ellipse at the periapsis and the apophysis. And let's say that I'm at a point over here. This is my position vector r. This angle will be f, my true anomaly. The eccentric anomaly is defined as I take this and hit the circumscribing circle like this. And I'm not going to give you the derivation of various formulas, but you can connect this eccentric anomaly to other quantities that we have been talking about. For example, the position is given as a times 1 minus e cosine f epsilon, or cosine f is given by cosine epsilon minus e by minus e cosine f epsilon. Right. There are also relations for the tangent, sine, and so on and so forth, but there's no point in giving you a whole laundry list. What is the geometric interpretation of E? And all of these, like this one, for example, directly follows from this geometric interpretation. You look at where this is, and you connect. You just recognize that you're just multiplying this by some factor and going from some A to B. It's like literally compression. You could also think of this as some projection. You could think of this as there's some sphere that's surrounding that you go to one higher dimension, like you're moving in the plane, but consider a sphere centered over here, where the radius is the same major axis, and you're moving on a geodesic flow, you're just moving on great circles on the ellipse. The projection of that onto the plane is going to be the ellipsis. And the projection angle is going to be your eccentric anomaly. It's going to have its cosine of eccentric anomaly, but you know what I mean. So that's one geometric interpretation, but this is how we define eccentric anomaly in general. The other one, that geodesic flow and so on and so forth, has some applications, but you know, we don't have time to go into those stuff. If that interests you, it interests me a lot. So just ask me. I'm going to. I can send you a lot of references regarding that. Now, another anomaly that we're going to define is, first we need to define the mean motion. So n written as 2 pi by t is called mean motion. So this looks kind of like some angular velocity, right? I'm taking some angle dividing by some time, so it looks like an angular velocity, and through this I can define the so-called mean anomaly. So this is the time of pericentric passage. So typically, you actually measure your time by setting your tau equal to 0. So this is just n times t. That doesn't really matter. And so this angular velocity, or average angular velocity, if you look at this is your average angular velocity, times time is going to give you the mean anomaly. And there's one equation that's quite important. I'm not going to go into this, but I'm talking about the Kepler problem. I'm not writing this equation as sin, so I'm going to write it down. Kepler's equation. This is called the Kepler's equation. And the derivation of this, using this and properties of eccentric anomaly, you can find in invariant Darmot. Darmot section 2.4, I think. I can't read my own handwriting. It could be 2.6, but it's close enough. So this allows you to find the position and the velocity. So eccentric anomaly also allows you to calculate your velocities, components of velocity, not just the position. But on the left-hand side, you have some simple time, something proportional to time, and some average velocity. On the right-hand side, there's a quantity that gives you the position and velocity. Right? So going this way is very easy. Given position and velocity, you can tell what time it is. But usually you want to know, given time, where your position and velocity is. And that one requires root finding again. But you have to invert this equation. And the way to invert that equation is again by the international method. And that one, again, has been solved for decades. It's one of the... I think like every couple of years, somebody comes up with a new solution still. A few years ago, somebody found a more efficient way to solve this equation. There's a lot of literature on this. Again, if you're interested, I will be happy to share references. Right, but these are things that you need to know when somebody is talking about the Kepler problem: the true anomaly, eccentric anomaly, and mean anomaly, and some basic relations, how these are related to these quantities relate to each other. Now, we are going to come back to this when we look at the Hamiltonian approach. So this is not all in vain. I'm just putting notes down here. I will probably review them. Don't worry too much. But it's not just that I'm throwing some information at you that we're not ever going to use. And come to Hamiltonian mechanics, we are going to look at celestial mechanics problems, and we are going to use these again. And so it's not just a laundry list that I think you should have an idea of. But there is one thing that you don't need Hamiltonian mechanics, which is quite fascinating and quite useful. We don't have time to go into details of this. I mean, to go into details of this would require a few weeks, but I'm going to talk about it very briefly, and that's Laplace Runge lens vector. By the way, I don't know how to read this gentleman's name. If anyone, actually, I don't know how to read any of these names. I call this Laplace, probably it's something else. I call this Runge. I mean, I think it's German. Lens, I have no idea where he's from. Yeah, this is a very important vector. Now, how does this come about? Yeah, I'm just going to give you some definitions, but there is something very strange. So we found that by solving, our central force equation with the potential like this, we found a closed orbit. The orbit was closed. Now, there is no reason why it should be the case. Okay? By our analysis, we said that, okay, there should be some minimum and maximum and so on and so forth. But in principle, these don't have to be closed ellipses. This could be precessing. Okay? This could be like going around this way, for example, as you rotate. But our orbit does not precess. Now, why? Why does it not precess? The reason is it possesses an additional symmetry. So the Kepler problem is one of a class of problems that are called over-integrable. Meaning that after you find all the integrals of motion, there's still something else to find. Okay? And you can approach this from, of course, other ways. You have complete freedom in choosing, which equations to integrate first. We could approach this from the Laplace Runge lens vector. We just approach it from angular momentum, simply because everyone is familiar with angular momentum. Yeah, but Laplace Runge lens vector also provides a complete description. There's another vector called Hamilton's vector that also provides an equivalent description, which we're not going to go into. So our equations possess a higher degree of symmetry, and consequently, they have an additional conserved quantity, in this case, a vector that fixes the position of the periapsis. Okay, this is what's going on here. And we're going to just try to investigate this. Now, first of all, what I just said, that this problem possesses a higher degree of symmetry, is so we have spherical symmetry, right? So this corresponds to some symmetry group O3. I don't know if I don't need to go into. I don't want to go into group theory because I don't know it, and some people here wouldn't know it either. But the spherical symmetry in 2 dimensions is a certain symmetry group associated with this, right? And that group is going to have that symmetry is going to have a number of conserved quantities. Our problem is a large number of conserved quantities. It feels like it's the rotation group in 4 dimensions. And it turns out that this is actually true. You can take a sphere in 4 dimensions and look at the geodesic flow on the sphere and take a projection of this into 3 dimensions, not just the projection like I was showing before. It is going to be a stereographic projection. So you take a point and you pass through the sphere and you put this on a 3 dimension. You can't draw this because it's from 4 dimensions to 3 dimensions, but if this was a lower dimension, it would look something like this. So you take this point and then you project on the sphere, something like that. And the geodesic flow one-to-one corresponds with the elliptical orbits. This result was shown very late, actually in the 20th century by Moser. And so there is something there. But these results were used by Pauli at the beginning of the 20th century to find the spectrum of hydrogen atom. And so this is one of the cases that you always say, okay, there is group theory, there's symmetry, or so. They always seem like they use them after the fact. Like you find some property and say, oh, it's compatible with the symmetry. But no, you can actually take the symmetry and use it to find some concrete result. And Pauli did this for the hydrogen atom. We don't teach this, but you can read the papers. They're a little bit hard to read. It's quite involved mathematically, but there are some applications. Right? And it's all related to this Laplace Runge lens vector somehow, because in the higher dimensions, you would expect an additional vector quantity to be conserved. Now, this vector I'm just going to write this down. There's some derivation in the book, but I'll just be copying it. I don't want to simply copy that. Just the Laplace vector. You also sometimes use this divided by mk, right? And this is the eccentricity vector. They of course have very similar properties. One is a unit vector, the other one is not. Now, so in the book, the general equations, without assuming the central force law, is, so where does this come from? Let me just very briefly show this. L is minus m of r r squared d by dt r by r. Okay. So this is the equation that you get by some manipulations, and this is in general, it doesn't lead to anything. But if this is 1 over r squared, then there's a cancellation, and you have two total time derivatives on two sides, which leads to a conserved quantity. The difference of these two, which is this vector, has to be conserved. And if this is not 1 over r squared, you can't do anything. I mean, you can, of course, integrate this and get a quantity, and sometimes you are going to get an analytical function and so on and so forth, but it's going to depend on theta and r in general. So there are analogs of this Runge-Lenz vector, or Laplace Runge-Lenz vector, I should say, for the other force equations, but they're not very useful. Okay? Because for other force equations, the orbit is not closed, which means your theta and r are just going to go all over the place. Right? You're not going to get a simple expression, and it's not going to correspond to anything interesting. Right? So, for example, one of my students tried to find this for a three-body problem, tried to find something integrable. He did come up with some expressions which we'll need to handle numerically, but it's still not interesting. It doesn't lead to any insight. Now, because A is given by this, A dot R, sorry. No, A dot L is 0. Now let's see if we can show this. So this one, when you dot it into L, it's trivially 0. Right? This one dotted into L has to be 0 because R is perpendicular to L, because L is R cross P. Okay. So this is 0. What does this mean? I have the dot product of two vectors to be 0. Well, this also must be perpendicular to L. So A lies in the orbital plane. The plane gets just swept by R. And in fact, it is, when you draw the plane, orbital plane, and your force center, it looks like a vector like this. Now it's a constant vector, and this is a closed orbit. It always points in the direction of the system. Okay. Right. Now, this has this Lagrange vector and the angular momentum define the orbit completely. Okay. Or the shape of the orbit at least. So A and L define the orbit completely. So what does this mean? So this is going to be my A, and my L, let's say, is going to be some vector pointing towards me. I have these two perpendicular vectors. Now, they determine the orbital shape, but they do not tell me where I am on the orbit. Okay? Now, how many parameters do I need to describe my position and velocity on the orbit? I need 6. There's no way around this. For an arbitrary orbit, I can be anywhere, I can have any velocity. So I need 6 parameters. And this has 6 parameters, A and L, but they're missing one. So you could think of this when you're thinking of the orbit. There are 3 angles that determine the orientation of the orbit. Okay, the orbital plane and how you're pointing. So 2 of them is going to define the orbital plane. One of them is how I put this orbit in the plane. So I can rotate this. There's that freedom. There's one angle there. And 2 is going to be the orientation of the plane. Now, one parameter defines the size of the orbit. That's the major axis. The other parameter, eccentricity, defines the shape of the orbit, how much you deviate from the circle. And one additional parameter tells you where you are on the orbit, your phase. So that's 6 parameters. And you could be x, y, and z, and the x, y, and z. Or it could be those 6 parameters, 2 for the orientation of the orbital plane, 1 for your orientation in the orbital plane, 1 for the size of the orbit, 1 for the shape of the orbit, 1 for your position of the orbit. So these define the shape of the orbit completely, but there are 6 numbers. Yeah? So one is superfluous, as it should be, because they are not completely independent. So this equation is like a constraint. It kills one of your parameters. So even though these come with apparently 6 parameters, that since they're not completely independent, there are only 5 independent parameters, as they should be, and they define the shape of the orbit completely. Your position on the orbit cannot be determined by the integrals of motion. Right? The integral of motion can never do that because that depends on your initial conditions. Obviously, that if you start a little late, you are going to be at a different point, and your integral of motion, the energy and angular momentum, and so on and so forth, are not going to change. Okay? Now, yeah, I don't want to talk about why this exists anymore. And in the last 15 minutes, I actually want to say a few things about the 3-body problem. So then perhaps we can finish. Yeah, this is, I think, all I want to say. So in the book, they are saying that the Laplace union length vector, the angular momentum vector, and energy define the orbit completely. That's also another approach, but they are not completely independent. There is a relation given in the book. I don't know if I copied this over here. I did not. So those are not independent either. So given these 2, you actually can tell the energy, as you should be, because given these 2, you can tell the shape of the orbit, and the shape of the orbit determines the same major axis, and given the same major axis, you can tell what the energy of the orbit is. So that's another way to approach it. I'm not saying it's wrong or anything like that, but I prefer to think just in terms of the vector quantities and forget about energy completely. As you will see, there are alternative ways to define the motion on an orbit, and these provide a very nice geometric interpretation. But yeah, they're not very widely used. There is the description of the orbit through these is called the Milankovitch variables. So let's mention that name. If you want to look this up, this is the keyword that you should look for. Right. Now, I want to talk a little bit about 3-body problem and finish. So, as you know, well, I don't know if you know, but as perhaps you know, the 3-body problem is not solved. Okay. So this was one of the prize problems by the King of Sweden and so on and so forth. And Poincaré showed that it's not solvable, and he got the prize. Or something like that. I'm not really sure. History is not my strong point, obviously. But there are some particular solutions for the 3-body problem. So if you are given in the book, so there's Euler's linear, is it collinear solution? Yeah, solution. And there is Lagrange's equilateral triangle solution. Solution. And there are other solutions that look very interesting. There's, for example, a figure-8 solution. Okay? There are 3 masses just going around in a figure-8 in a stable configuration. This is another solution. There are a whole family of orbits that's related to the figure 8 solution for 4 bodies, 5 bodies, and so on and so forth. But these are not physically interesting. These don't happen. Okay? No 3 celestial bodies are going to end up on equilateral triangles or completely in a line. And if you deviate from the assumptions over here, they immediately go away. There are some exceptions for the figure 8. There's a region of stability for figure 8 configurations, but again, if there's another additional perturbed body, all that delicate balance gets broken. There is, however, one particular solution, and that's the restricted circular three-body problem. Now, what does this mean? Well, I have M1, M2, and M3. And let's just assume M1 is larger than M2, and M3 is a test mass. So that's the restricted part. The circular part is M1 and M2 are on a circular orbit. So let's say this is M1, this is M2. One. And I'm just going to call this O. These are rotating with some angular velocity omega around the common center of mass. The center of mass is closer to M1 because by my assumption M1 is larger than M2. And I have a test mass somewhere over here, M3, and the motion of this test mass is sometimes interesting. Now, why is this relevant? Because we have this situation. We have this situation in our solar system. One example would be that this is sun. This is Earth. Let's say this is Moon. Moon is approximately in a circular orbit around Earth, and that could be some test body that's moving around. Okay? So this Earth-Moon configuration could have additional bodies coming from asteroids, something like that. And we want to look at their behavior, how they get affected by this rotating potential. Another one, this could be Sun, this could be Jupiter, and again, this could be asteroids. And this is in fact observed in the so-called Trojan asteroids of Jupiter. Saturn has its Trojan asteroids. The other planets also have some. I think Earth doesn't have one, but a lot of planets in our solar system have the Trojan asteroids. So for some configurations, this is going to be stable. And so how can this be stable? Right? So that's one thing. That how can you start a situation like this that looks crazy and just stay in that position? Well, we can have, first of all, 3 points that are collinear and just has some delicate balance that if you're at those points, that we can stay at those points. So these have names. These are Lagrange equilibrium points. So this is L1, this is called L2, and this is called L3. Now you can try to find the location of these points for a test mass by simply saying that, okay, I'm going to have some rotational motion. At what point the vector sum of the two forces coming from these masses is going to give me the required centripetal force. If the sum of the two forces gives me just enough acceleration that my centripetal acceleration is going to lead to an angular velocity, a uniform circular motion with omega, then I'm just going to stay there. And it can be done for these 3 points. And we use this for the Earth and Sun system. Like I think there is a satellite at the L1 point of Earth that's looking at the Sun. And it's very convenient because it doesn't move away from Earth. We can always communicate with it. It doesn't go to the other side of Sun. And well, it's closer to Sun. We can just look at Sun and get a lot of data. And there are satellites that are over at L2. Again, these are now outside the atmosphere. They're not on orbit around Earth, so they can be made more stable. I don't think there's anything at L3. I mean, there could be something at L3, but we didn't put anything there deliberately. but there is a logic putting some satellites on L2 as well. And I'll come to that at the end. There are also two more points over here. So if you're taking this way, the upper point is called L4, the lower one is called L5. These are the 5 Lagrangian points. Now, how do you get the solution? How do you get the equations? And how do you attack the stability? Well, you write the Lagrangian. So this is a half m r dot square plus r square theta dot square minus u of r theta and t. Now, our Lagrangian only, so m is m3. Our Lagrangian only involves m3 because these guys are just, moving on circular orbits. I can add their kinetic energy, I can add their potential energy to the system, but it's not going to change anything. I'm just doing a constant. Right? They're just moving on circular orbits. They're not doing anything. There's no exchange of potential and kinetic energy between them. You want me thinking about what about the effect of M3? Right? As M3 moves around, aren't their potential energy going to be changed? No, because M3 is a test mass. That's the whole point. Okay? So because of this, I'm not including their energy. It's just going to shift my Lagrangian. There's no effect. And I'm just going to include kinetic energy of this. And this is the time-dependent potential energy that's created by M1 and M2. In general, it's going to be a function of R and theta and T. Now, what we do is that from R and T, by the way, this is the center of mass is going to be our origin. That's most convenient. But from this R and theta, we are going to go to rho theta prime and z. Let's just say rho theta prime. This theta prime is going to be theta minus omega t. So we move on to the rotating reference frame. In the rotating reference frame, these two are going to be fixed, but we are going to have fictitious forces. We are going to have additional forces, additional terms in our Lagrangian. So let's write those terms down. So this is now going to be a half m. These are the spherical coordinates, right? Rho theta and z. And rho prime square plus rho square theta prime dot minus omega squared plus z dot square minus something. I want to keep z. I could just get rid of it. I could say that, okay, my motion is still in the plane because there's nothing interesting happening outside the plane, but that's not so. So if I look at the stability of these points and the motion around these points, so like you could go this way around some of the points. So I'm going to keep z, but we're going to make use of it when we come to stability after we look at the oscillations. Okay. And we can open this up. This is going to be a half m rho dot square, rho square theta prime dot square plus c dot square. This is what you would have normally. And now we are going to get some modified potential, some effective potential. This is m omega rho square prime dot minus half m rho square omega square plus your v.
Hocam, is that z in the equation?
Yes.
Okay.
Yeah.
It is we are assuming we are in a cylinder like a polar coordinates. And
yeah. So I went from these coordinates to the cylindrical polar coordinates.
Okay. Thank you.
And I just went to the rotating reference frame. I'm simply replacing this by omega theta minus omega t. Now this. Now we could call our pseudo potential. Okay. In fact, that's what it's called in celestial mechanics. And this has two additional terms. Now this one is something we're familiar with. This is the centrifugal force, the fictitious force in the rotating reference frame. This one is the Coriolis force. So we are going to skip over the rigid body motion, but we are going to do it enough to get these forces. So include them in your pseudo potential, and when you're trying to calculate your force, you should use these. And this is going to come handy when we make the stability analysis. And I'm going to leave that for now and just try to show you something that I find really fascinating. So this one, these guys, the L4 and L5 points, along with the position of the masses, they form a triangle, right? And let's just call this side an A. What did I call this? I call this one B, actually, and this one C. And let's call this one D. Now, I want to find the location of this point, L4. And so if you try to find the location of this L1, L2, and L3, you're going to find some equations, but they're not simple quadratics. They are cubic and fifth order equations for which you can, of course, write down the solution. But it's not something very simple. Turns out for these points, it is simple, that you can write some simple expression. I'm going to show the first few steps of this derivation. This is not in the book, but it's a shame it's not there. So I'm just gonna do this. So this little test mass is feeling two forces, F1 towards 1 and F2 towards mass 2, and these are going to add up to F. F1 plus F2. And eventually this has to be the centripetal force that's making me go around with this angular frequency omega, if that's a stable configuration. Right? Now, I'm going to turn these into vectors. So this is going to be A, this is going to be B, and this is going to be C. So A is the position of M1 with respect to M3, B is the position of center of mass with respect to M3, and C is the position of M2 with respect to M3. They are all vectors. Now, B can be written simply as M1A plus M2C divided by M1 plus M2. And you can rearrange this and get M1 A minus B is equal to M2 B minus C. Now I'll take this and take the cross product with F, which is F1 plus F2. Okay? Now the cross product of F with B on the two sides is going to be 0. So the B terms drop out, but the cross product of F1 with A is going to be 0. So that one drops out. I'm going to end up with the cross product of A with F2 over here. So let's write that down. This is minus M1 F2 cross. Oh, I start on. This is A, I think. Yeah. And on the other side, again, this F is going to get completely cancelled by B, and C is going to get cancelled by F2. And so I'm going to end up with F1 C term. This is going to be M2 F1 cross C. Now, the angle between F2 and A is this angle, and the angle between F1 and C, this is F1 and C, are the same. They are opposite in some sense, but they are the same. So the magnitude of these two vectors must be the same. So this is just, M1 F2 times some angle factor, and this is M2 F1C times the same angle factor. I'm just going to drop that angle factor. So I'm going to write it like this. Let's see. And so same angle. And now I can substitute the values for these. So this one is M1. What is F2? Well, F2 is this is a test mass, so I'm going to just drop this. It's M2 divided by C squared times G. 2 by C squared. I hope I'm getting this right. A, and this is F1. F1 is sorry, M2. This is M1 by A squared times C. And then M1, M2 is cancelled, and I get A is equal to C. Okay? So this is an isosceles triangle. These two angles are the same because A is equal to C. Only when they are equal to each other, only when it's an isosceles triangle, these two forces are going to add up to force pointing in the direction of the center of mass. Now, there's a more involved algebraic thing you can do, and you can also show that this is equal to D. Okay? I'm not going to do that. It will take much longer than this. But you can also find it in Murray and Dermot. And like any celestial mechanics book, really, Fitzpatrick, Murray and Dermot, whatever. And so this is, in fact, an equilateral triangle. Right? So I find it very surprising that the collinear problem is harder to solve. You can't solve it exactly. I mean, you can't write down the solution exactly. But the triangular problem is just an equilateral triangle that you can write down yourself. It involves some algebra, obviously, but well, apparently Lorentz was up to the task and he did carry out the steps and found this result. Okay. So I'm not going to discuss scattering at all. I don't know how to do it briefly, so I'm not going to do it. But if you need that result, if you need anything from the sections that we skipped, we are just going to quote the results without doing any proofs. So don't worry about it. Any questions? This. All right. So